my screen. However, I am not able. There is maybe some technical problem.
Just a second, Mariusz. Yes.
Mm-hmm.
Okay, you can share now.
All right, that should work. Can you see it?
Yes, very well. We see full screen and we hear you. Please go ahead.
All right. So good morning, everybody. My name is Mariusz Sapinski. I'm actually now working for CIST Foundation, so working on this new magnificent accelerator for hadron therapy. And today I will introduce you to some aspects, crucial, critical aspects of accelerator physics. Here is the contents of my presentation. So the presentation, what I'm going to talk about now is here on the left. I hope you see my mouse. I will introduce a little bit of history and of accelerators and motivate why we need them, not only in medicine, but also in science and in the industry. Then I will talk about the beam properties, what is a beam and what are the properties. And there will be some part about RF acceleration, longitudinal dynamics, phase stability. Then we will talk about cyclotrons and synchrotrons, so circular machines, and about strong focusing and transverse dynamics and beam transport. This talk will be followed by two other talks that I will give later this week on Wednesday on beam instrumentation and on Sarajevo LINAC project on Friday. However, this week is full of interesting presentations related to accelerators. You have seen already yesterday two presentations from Maurizio. Then tomorrow there will be a presentation about linear machines from Giovanni. Special aspects of synchrotron operation, which is injection and extraction by Elena and Rebecca. Nadia will talk about ion sources. Presentation of Nadia is actually split in two. There is a part today and part on Friday. Then Elena again will talk about gantries and beam delivery. Low energy accelerators will be presented by Milko, and there are two students from Sarajevo who will present their work on related to Sarajevo LINAC project, which is ion beam analysis presented by Fahima, and Benjamin will talk about low energy beam transport simulations. All right, I wanted to start kind of broad and tell you about what science is, what are the approaches of science to get evidence about the reality. Basically, there are two approaches. One is observation of nature, the other one is controlled experiments. If we talk about sciences like astronomy and physics, then typically you would say astronomy is observing the nature and physics is performing controlled experiments. This is not completely true because physics is also doing a lot of measurements by observation of nature. Some of the elementary particles like muons were discovered in cosmic rays, so by observation of what comes from the space. And this also continues. There are experiments, we call it experiments, but actually they sit there and wait for events to happen from outside. And here you see an example, a device which is called xenon detector, which is sitting underground deep and waiting for dark matter particles to come and interact. Well, but coming back to experiments, we have many different types of experiments. The methodology of experiments is very rich, and we have various tools. And some of these tools are more important, some less important. For instance, very important tool is laser. It's a device that was discovered or constructed in 1950s, and since then is a very important tool basically in almost all experiments. Sometimes it's the main tool in the experiment, sometimes it's kind of secondary additional tool, but it's nevertheless used in experiments. The other tool like that are accelerators. They are also extremely important. It's not the only tool we have, but it's very, very important, and I will try to show you this in a few slides. There is also another tool, which are microscopes. Optical microscopes, they were invented in the 17th century, and you see here a drawing of such a microscope. The resolution, so the ability to distinguish 2 points nearby is around 200 nanometers. It's very, very little. Huh? let's think that the human hair is, let's say, 50 micrometers diameter. So we are much below the human hair size. This resolution is determined by the wavelength of the optical light. There is something which is called diffraction limit. So at this limit, the light spreads, and we cannot really reconstruct anymore 2 points being one next to another. And optical light wavelength is between 400 and 800 nanometers, what explains that the resolution is 200 nanometers. So this is good for bacteria. Bacteria were actually first seen by by optical microscopes, and the typical size is somewhere between 0.5 micrometer to 2 micrometers. However, the famous virus that destroyed or altered our lives on the planet recently has a size of only around 100 nanometers. So it is well below the resolution of optical devices. Let's not forget the resolution doesn't mean we can create the image. Huh? Resolution is just we can distinguish 2 points. So actually, we are quite far from what is needed. In order to go to higher resolutions, of course, we could decrease the wavelength. Decreasing the wavelength means going to ultraviolet or X-rays, and that was actually proposed already at the beginning of 20th century. The problem with decreasing the wavelength all the way to X-rays is that we actually don't have optics. We don't have these lenses that are inside the microscope for X-rays. So we cannot really reconstruct images. However, by diffraction, we can reconstruct, for instance, the crystallic structure of the crystals. Like on this plot here, drawing, you see a crystallic structure of a diamond, and this can be described or discovered, measured basically by so-called X-ray crystallography. This X-ray crystallography was invented by two Braggs, father and son, in 1912. And what is interesting that the father is the same person who actually first discovered the Bragg peak. It's called Bragg because of this guy. This Bragg peak was discovered in 1903. We heard about Bragg peak a lot yesterday. We will hear even more during this week. All right. So X-rays are not very good for microscopy. What can we do else? And another PhD student, actually, yesterday Maurizio said that there was a PhD that led to linear accelerators. And actually in 1924, a PhD student, Louis de Broglie, which was a French physicist, he proposed a so-called wave-particle duality. In this proposal, he says that electrons in certain conditions, they can behave like waves. If they can behave like waves, we can use them as a light, because light is a wave, and therefore we can reconstruct images using electrons. So this was 1924, and already in 1931, a German engineer constructed the first electron microscope. And here on the right figure, you see actually an image from such electron microscope. And what you see on the image is still related to accelerators. It's a carbon fiber which was irradiated in the SPS beam. SPS is one of the CERN accelerators, if you remember. The diameter here is around between 5 and 10 micrometers. I think it's actually 7 micrometers. Electron microscope can reach the resolutions which allow basically to see single atoms, 0.1 nanometer, so 1 angstrom is basically the size of the atom. And they work on normal objects. You don't need to have a crystal, right? They actually do microscopy. What if you want to look inside the atoms? Well, photons and electrons, they're interacting with other electrons in the atom. So you need something heavier, some particle which will not be stopped by this electron shell in the atom. And that was the idea already we are still in the beginning of 20th century, right? I think all physics students heard about the Rutherford experiment, which is shown here. We have radioactive source here, which is emitting alpha particles. These particles are hitting gold foil, and they are scattered. And some of those particles actually scattered back, which means that in the atoms there is some very hard core, which we call nuclei. Those type of experiments were performed all the way beginning of 20th century using alpha particles with energies several MeV, and they also led to the discovery of protons and neutrons. And of course, there is limitation. Limitation here is that the beam of particles, so we already have a beam of particles without the accelerator, is produced by this radioactive decay, and we have no control on the beam properties. We can collimate it a little bit at the beginning because we have a hole in the shielding. However, we cannot really change energy in this setup. We cannot, we cannot do many things. So the need to do something with these beams was the beginning of accelerators. So why do we like accelerators? Why do we use them for physics? Since Rutherford, these accelerators were very much developed, and basically most of the progress in nuclear and particle physics is thanks to those devices. The progress is measured in discovery of new isotopes, often short-living isotopes, which give us insights in how nucleon is made. Sometimes, or very often, they actually do not exist in nature, like we discover new particles and actually we don't observe them in nature. So why producing new matter from energy, thanks to E equal mc squared, which is the famous equation, the most famous equation in the world? Why is this important for us? Why creation something that does not exist in nature is important? I mean, it doesn't exist, it doesn't affect us. Well, it's not so simple. First, because all those particles that were created that exist only at very high energies, right? To create them, you need a lot of energy, and then they disappear. Those particles really existed everywhere at the Big Bang, at some very beginning of our universe. And this changed our world, this changed how the world evolved. But it's not the only reason. They also exist actually now. We are inside the sea of those particles, which appear only for a little moment. And here you see a Feynman diagram of neutron decay. This is a neutron. Neutron is made of 3 quarks, up quark and 2 down quarks. And one of these down quarks decays into up quark by emitting electron and neutrino. This decay takes around 11 minutes. It's a very long time for nuclear reaction. Nuclear reactions are very strong. Why it takes so much time? Well, to understand it, we have to go and see that this decay goes through a particle which can exist only for a very short time because its mass is 80 gigaelectronvolts. So it's 80 times the mass of the proton. If this particle were lighter, then actually this decays would happen much more often. And our world would be completely different. So in order to observe this particle, we actually need to create it. So here it exists for a very short moment, and it cannot really be observed because let's simplify it a little bit, we call it a virtual particle. So we cannot observe it. In order to observe it, we have to actually give it this 80 gigaelectronvolt energy. And in order to give it this energy, we need accelerator, which has, SPS has 6 kilometer circumference. All right, so I hope now you understand we do need accelerator experiments if we want to understand the world around us. It's not something fancy that we do with very large machines. We actually want to understand how the world works. But this whole week is not really about accelerators in particle science or nuclear physics. It's about accelerators in the industry and in medicine. And I'm not going to go through this slide even because there will be so much more during the week about these applications, of course, especially in medicine. All right, so let's think, what is a beam? Accelerators are producing beam, so what is a beam? We already said that the beams in principle can also be produced by radiation source by just collimating the radiation coming out of the radioactive isotope. So basically, it's an ensemble of particles which are moving in the same direction. This ensemble of particles can be characterized by the particle type, and usually we use one type of particle at the given moment. So either electrons or protons, there will be a slide about that. By the intensity, so the amount of particles which are emitted which is traveling in the beam, by the energy and energy spread, and by the transverse size and divergence. So now I go a little bit more in the details. Particle types, basically we can create beams of any particle you can imagine. The easiest were electrons, and they were created already in, I think, 19th century in X-ray tubes. So at the time, they were just, before discovery of X-rays, these tubes existed. Antiparticle of electron is a positron. We also can do this kind of beams without any problem. Protons and antiprotons we do all the time. Then we come to ions, and of course here the special interest are the ions which are used for medical applications. So for instance, helium ions or carbon ions. We can easily produce them and form beams out of them, but actually we produce ions of all possible states. There are also exotic and radioactive beams, like for instance there are beams of helium-6, which decays very fast in fraction of the second. There are beams of negative ions, which are actually very useful for high energy, high intensity machines. There are beams made of compound particles, for instance, methane beams. So CH3+ is used in some machines in initial stages to actually obtain very high intensity beams. And at the end, we also have beams of neutral particles. Those beams, they can only be produced as a secondary beams. Neutral particles, we have no really way to control them. So we can produce those beams, they go somewhere, and that's it. And one of the most interesting are beams of neutrinos. And here you see a beam, which is basically from the source to the detector is almost 300 kilometers long. This particular case is in Japan. It comes from J Park, goes through the Earth. So neutrinos, they are almost not interacting. Therefore, we don't need a vacuum chamber to guide them. After 300 kilometers, they hit a detector. Of course, most of them go through the detector because they don't interact easily with the matter. But yeah, we have this kind of beams. All right, what are the beam energies? Energy is conveniently expressed in electron volts. It's the energy that the elementary charge gets in 1 volt potential. And for ions, we really like to talk about electron volt per unit mass, so per nucleon. That's for many reasons. Lot of formulas are getting simpler if we use this unit. For some studies, particles are actually decelerated. So accelerator can also be used in the inverse mode and decelerate particles, and they go all the way down to milli-electron-volt energy. And sometimes they are even trapped. So for instance, at CERN, there are experiments, or many other laboratories, there are experiments where antimatter is trapped and even stored in some kind of magnetic traps for hours, if not days. On the other hand, we have the highest beam energies per particles. And here, of course, the king is a Large Hadron Collider at CERN, which produces proton beams at energy of 6.5 tera-electronvolt. Tera-electronvolt is on the scale here. This is the energies which are produced by LHC, is 6 times 10 to the 12 electronvolts. So if we have, yeah, it's very large energy, all right? However, it's not the largest energies that we observe, because what you see here is a spectrum of cosmic rays as registered by various detectors on Earth and in the space. And you see that it goes all the way up to 10 to the 20 or 21 even electronvolts. So nature finds ways to accelerate particles to much higher energies than what we can do in our biggest laboratories, way several orders of magnitude higher. Actually, this very high energies, one of the particles that was observed in I think 1991 is called Oh My God particle, and energy of this single particle was 50 joules. 50 joules is something you can feel basically easily. It's hot. If the 50 joules is translated to your hand, you feel really hot. All right, so this is energy of a single particle, but then there is a total energy stored in the beam, and Maurizio was talking about it also yesterday. He mentioned the number 362 megajoule. This is the energy stored in the LHC beam, and this is equivalent of 77 kilogram of TNT, or equivalent of kinetic energy of of very fast train in France. All right. Now, in the beams, we don't care only about the maximum energy, but also about the energy spread. And typical energy spread, we actually prefer to talk about momentum spread, but it doesn't matter at this point. The typical energy or momentum spread is of the order of 10 to the minus 3 in the machines that we are using. It's an important number. It will come back later. Now, the beam intensities. So beams are produced by ion sources, and ion sources, they produce, at least the ion sources we are using, they usually produce continuous beams. And as we will see later, the beams is bunched in the accelerating structure afterwards. The ion source intensity is usually given in milliamps or microamps, and typically we have intensities of several hundreds of milliamps. These are the intensities we are using in hadron machines. But once we start accelerating the beam, especially when we inject it into circular machine like a synchrotron, then it's easier to talk about number of circulating particles. So these two things are kind of equivalent, but you have to get used that sometimes the beam intensity is expressed in the current units, and sometimes it's expressed in numbers of circulating particles. And ion sources, I think maybe Nadia will talk about it more, they can reach very large current, 65 milliamps, it's very large current of particles. And the number of circulating particles can reach any number between 1 and 10 to the 14. It's quite amazing, right? We can have actually one circulating ion or electron, and we can even measure it, or we can have 10 to the 14 circulating particles, enormous number, and we can also measure it. Here actually is a very interesting measurement. It's in GSI from ESR, one of the storage rings, which is used for precise measurements. And this is image of two ions circulating at the same time in this machine. They have the same momentum to charge ratio, so they can be stored at the same time. And you see basically one of them circulates over, let's say, this period of time, then it disappears because there is no perfect vacuum, so there's a collision with the gas. And the other one is circulating for 60 seconds, and actually it disappears because the scientists decide to kick it out. All right, the punch length is a different story. Let's go to the beam size. So the transverse size of the beam is again, there are many different sizes, and it goes from nanometers, which are the typical sizes of electron beams used for lithography to produce electronic chips, all the way through, let's say, centimeters, which are the typical sizes of beams in hadron therapy systems. We can focus them afterwards to millimeters, that's what we do, but the circulating beam is usually has a size of the order of centimeters, and the neutral beams, they can be of the size of meters or tens of meters even. Beam size is actually changing. You will understand why when beam is traveling through the accelerator. So it's better to talk about the beam emittance. And here is the first important term, the first important concept that you should know about. What is a beam emittance? First, look at the beam phase space. Phase space is here constructed from positions of particles and angles at which the particles move inside the beam. All right, and so each point is one particle in the beam, And each particle has a certain position with respect to, let's say, center of the beam. We will talk about it a little bit more later, and moves with a certain angle. Beams are always a little bit divergent, right? So it moves with a certain angle. And all these particles, they form in the phase space this kind of cloud. And the surface of this cloud, or because the cloud doesn't really have well-defined borders, so we usually say the surface of 90% of all the particles is called the beam emittance. So it's obviously related to the beam size. If you project the beam emittance on the axis where there is a position of particles, you will basically get a beam size. This is of course true if the beam has so-called Gaussian shape. So it has a Gaussian distribution in position and in angle, and most of the time is actually the case. All right, it is important to say that actually a lot of times people use, or we will also be using, so-called RMS emittance, which contains only 66% of the distribution, and it is one root mean square or one standard deviation of the Gaussian distribution. And a very important thing, in lack of acceleration or dissipative processes like, let's say, collisions with rest gas, the emittance is constant. It's not changing. Okay, so the particles are circulating in the machine, and the emittance is not changing. So this is the image of the beam phase space, and there are three ellipses drawn here. One is for converging beam, one is for beam waist, and diverging beam. Let's go to this ellipse, which is similar to the one you've seen before. Here you see that so this is the beam center. If the particle goes away from the beam center, then the average angle at which the particles travel is negative. So the angle is towards the beam center, okay? So obviously this kind of beam ellipse shows the converging beam. This is a diverging beam because more away you go from the beam center, the particles are even more travel with larger angles. So this is a diverging beam. And this is a beam which is, we call it sometimes parallel beam or beam waist. It's a place where beam is traveling in a parallel way. This is important to understand afterwards the beam transport in the machine. So we will come back to it at the end of the lecture. All right, when you accelerate particles, actually what is happening is shown here on this plot. So the beam starts to move with higher velocity in longitudinal direction, while the transverse motion doesn't change. So it means that actually the emittance, so the angle here, right, which is part of the phase space, is smaller. So the emittance actually shrinks. So acceleration shrinks the emittance. I think it's shown here, but yeah, this is the video of the beam shrinking during the acceleration in LHC. I don't know if it's well visible. This is real data from LHC from the first run. So the acceleration, here you see the energy, goes only to 1.38 tera-electron volt. If you multiply this emittance by relativistic beta and gamma, then you get something which is called normalized emittance. And the normalized emittance is conserved during the acceleration. The units of emittance is millimeter milliradian. Typical values for medical ion beams is somewhere between 0.5 and 1 millimeter milliradian. But the smallest emittances, they are really small. They can reach several orders of magnitude less, like 1 million times less, 1 nanometer milliradian. All right, I hope at this point you understand a little bit that how important is the role of accelerators in our civilization. You have a little bit of overview of variety of beams which are produced in the accelerators, and you get familiar with the concept of beam emittance. Let's now go to some details. Now I will sometimes skip some slides because some of them were already explained by Maurizio, and some of them will be much better explained in the course of the week. But let's talk about what kind of forces we can use to accelerate or control the particles. we have basically two forces, electric force and magnetic force possible. Electric force acts along the field lines, all right? Yeah, it acts along the field lines. Let's stop here. Now the magnetic force is actually perpendicular to the field lines. Somebody is speaking. I'm not sure if I should do something.
Continue. We will try to mute all participants.
All right.
Yeah.
Yes. Oh, sorry. I think I quit the presentation, unfortunately.
Yes, yes, you don't share now. We muted the participant that had opened the microphone, but we lost your screen.
Yes, yes, I'm sorry for that. I will try to go back to it. There is always some mishap during the presentation.
And we would like to ask the participants to please keep your microphones off and your cameras off. We are 290 people now on Zoom.
Yeah, can you hear me? I'm sorry for interruption.
Yes, we can hear you, Mariusz.
Yes, sorry, I'm coming back to...
Don't worry, if you have any problems, we can share it from Indigo you have uploaded. Okay.
Yeah, I didn't because there are some...
Yes,
anyway,
yes.
okay,
we see
anyway.
full screen. We see full screen and we hear you. Please go ahead.
Sorry?
Please go
Everything
ahead.
is okay.
It's okay. Very good. All right, so we have this electric force and magnetic force. A magnetic force is perpendicular to the field lines and to particle velocity. So basically, we cannot use it to accelerate particles because it's always perpendicular to the velocity. So all what is left is electric force. However, what is maybe very interesting is the magnitude of the force. So at electric field that we have in modern accelerators, let's say 20 megavolt per meter, a charge, elementary charge, feels a force of 3.2 piconewton, very small, but okay, it's elementary charge, elementary particle, very light. The magnetic field at very low energies, 20 keV protons, typical magnetic field is 1.5 Tesla, is only about half a piconewton. So it's even smaller than electric field. And this is important because you will see later that at low energies, we often use electric devices to control the beam. Why at high energies, we like to use magnetic devices, magnets. That's because when the velocity of particles of a proton goes towards the velocity of light, we are getting forces of around 70 piconewton. It's actually not completely true because I didn't use really relativistic formula, but this force starts to be really, really big. All right, so there is electrostatic acceleration, but I will skip this part because it will be much better explained in course of the week. So I will skip this slide. And this slide shows the RF resonant acceleration. Here, I will also not go into details because I think you remember this is from Wikipedia and Maurizio has shown it yesterday. I leave it in the slides because it may be good if somebody reads the slides afterwards. So this is the acceleration technique, the RF acceleration that was explained afterwards. We have these drift tubes and acceleration happens in the space between, in these gaps between drift tubes. Everything is in a huge metallic tank, and this metallic tank is a resonant tank. So we do the acceleration at certain frequency, and we enclose the acceleration system in the resonant tank, which has the same resonance frequency. This is important because we are talking about hundreds of megahertz. And well, if you switch on your radio, some of the stations are around this megahertz region. So obviously, megahertz waves can travel very far and can be emitted quite easily. So we have to enclose accelerator in order not to lose all the energy we are pumping in accelerating particles. Okay, then it was also explained by Maurizio yesterday. that nowadays there is a tendency to go to higher and higher frequencies. When we go to higher accelerating frequency, then we are usually gaining on gradient, and also the size of the devices of accelerating structure decreases. So we get smaller accelerators and more efficient. However, for instance, the problem is we still have to cool those machines, and it starts to be problematic. All right, now this is something I would like to explain, is the phase stability concept. It's actually a very important concept. In the acceleration, in this RF acceleration, we have a sinusoidal accelerating field, right? On this picture, you have phase of the oscillation of the field and the field amplitude. So sometimes the field is positive, is accelerating particle, and half of the time it's actually decelerating particle. This is actually how the accelerator works. But we want to accelerate particles. Can we do it all this positive side of the oscillation? Well, we cannot really. Let's imagine that we have particles in this point M2. In the particles, they always have some energy spread. That's what I mentioned before, around 10 to the minus 3 energy spread. All right, so it means some particles, they move a little bit faster and sometimes move a little bit slower. Those who arrive earlier, they actually on the phase plot, they are somewhere here in this point, N2. So they arrive earlier, and if they are in this point, they are accelerated more because amplitude here is larger than here, this reference amplitude. The ones who arrive later, which have smaller energy, they are accelerated even less. So this working point is unstable. The particles which will be in this working point, they will spread. They will go away from a stable phase. This point is actually stable because the particles which arrive earlier, which have higher energy, they gain less energy, so they move towards they are later in the next accelerating phase, accelerating period. All right, so this we call phase stability, or sometimes we call it also longitudinal focusing, and it means that our particles, they have to be placed somewhere here in order to be efficiently accelerated through a linear or circular machine. For synchrotrons, so circular machines, the image is a little bit more difficult, but I will not go to the details. But there, the orbit of the particles depend on its energy, and actually sometimes this point is stable, and sometimes this point is stable, depending if we are in relativistic or not relativistic regime. All right. So if the particles are sometimes too early, sometimes too late, so they phase changes. When the phase changes, the energy also changes. So basically particles in the bunch, or now we will define a bunch on this slide in a moment, they oscillate. They arrive a little bit too late, they get bigger kick. Yeah, so this is the time of the arrival or a phase. They arrive too late, they get bigger kick. The energy increases. Yeah. When the energy increases in the next passage through accelerating gap, they get smaller kick, so the energy decreases and they start to arrive later. Particles constantly oscillate, and this kind of longitudinal oscillation is called synchrotron oscillation. The name comes from the synchrotrons. It's mainly because it's quite slow oscillation, so we may not see it in linear machine, but in circular machine, where the beam comes back many times to the cavity accelerating structure, we actually see it. Now the particles are oscillating. So here is one particle. If you plot all the particles in the beam, you will see that they create this kind of cloud in the space of time and energy. So again, as with the position, transverse position and angle, we have a phase space. This is a longitudinal phase space. And the particles which oscillate here are stable within some phase and some energy. Here I replace time and phase because they are replaceable in case of our RF acceleration. And this phase space area is called longitudinal emittance. So here you have the second very important point. You have transverse emittance before, and now we defined longitudinal emittance. And you will see here there is what we call a bucket, which is the space where particles can be accelerated, or the range of phases where particles will be accelerated, and the bunch, which is actually the part of the phase space which is filled by the particles. For longitudinal emittance, the unit is electron volt second, and it's usually the values I didn't put here, but of the order of 1 electron volt second, or yeah, this kind of units. All right. So we already introduced the concept of linear and circular machines, and this is the diagram that was shown by Maurizio yesterday. I will not discuss it here. I will say a few words again about cyclotrons. Maurizio already explained quite a lot cyclotrons yesterday, but they are very important. Most of the hadron therapy machines are actually cyclotrons. They were discovered, they were proposed in 1929 by Lawrence and built by Livingstone in 1931. Here is actually the very first cyclotron ever built. It has diameter of only 10 centimeters, and it can accelerate protons to energies of already 80 kilo electron volt. How it works? Yeah, it has these two Ds, so very special electrodes which are empty inside, and there is a certain the polarization of the electrodes change with certain frequency, and the particles are accelerated in these gaps, and of course there is a magnetic field which makes particle trajectory circular, or rather spiral. The trajectories of the particles is defined by the balance between Lorentz force and centrifugal force, and fortunately for us, we can run these machines with a constant frequency, which is defined by the charge of the particles, the magnetic field of the magnet, and the mass of the particles. So this was the first idea. And now, of course, people have built much more complex cyclotrons. Here you see one of the most powerful cyclotrons in the world, which is in PSI, near Zurich in Switzerland. It has 4 accelerating cavities, 8 magnets, so it's already sectored. It's not one big magnet. There are 8 magnets. And it can produce protons at energies 590 mega electron volt. The power of the beam, so the amount of energy carried with the beam per unit of time, is huge. It's 1.3 megawatt. All right, and proton cyclotrons are really a workhorse for hadron therapy. Most of hadron therapy devices are small cyclotrons which accelerate protons to 230 mega electron volts. The limitations, of course, is that energy that you can achieve is limited by the fact that at some point the mass of the particle starts to depend on the energy. We start getting relativistic effects, and then we have to start modifying the way the cyclotron works. The radius at which the particle spiral gets larger and larger. And so at some point we have to have very large disk with vacuum, and it's really not practical. So at some point we need a different concept of producing high energy particles. All right, now I say a few words about betatron, because that was the kind of step between cyclotrons and synchrotrons. Electrons are immediately relativistic because they are very light. Therefore, we could accelerate them in a device which works this way, that it has one magnet. Here we have a magnetic field. When we accelerate electrons, we actually ramp the magnetic field to keep them on the orbit. And when we ramp the magnetic field, we actually produce electric field, the vortex electric field all around the accelerator. So it's very nice. You know, we have circular accelerator, not with one cavity, but acceleration is happening in the whole circumference of the accelerator. And these devices are called betatrons, or were called betatrons. They are not really used anymore. They are not very efficient. They could produce electron beams up to 300 mega electron volts. Interestingly, similar idea of acceleration is nowadays still used in Medaustron and in CNAO. It's called the Betatron core, and it's a device which generates accelerating electric field by this equation. So it's kind of vortex accelerating field. All right, now we come to the synchrotrons. Because of course betatrons were limited, so the idea is let's split the magnet in the betatron into many magnets, and let's use much more efficient RF acceleration. The first idea was from Russian scientists in 1944. At the time, the communication between in the world was not very good, so it was rediscovered by Macmillan in 1945, and the first proton synchrotron was built by Marcus Oliphant in 1952. Okay, so we split the magnet. We divide. Actually, we have separate magnets for focusing. We will talk about it, for bending, and separate cavities or accelerating structures for the acceleration. What is important, where the name synchrotron comes from, is that the field of the magnets changes with the beam energy synchronously. All right, so this is where the synchrotron name comes from. And now a few words about the future. Again, it was already mentioned yesterday that there is a way to produce much higher accelerating fields than what we can do with RF acceleration. The best cavities currently can reach 50 or 60 megavolts per meter in kind of laboratory conditions. In regular operation, we are rather limited to around 100 megavolts per meter. I don't remember what is Click doing, but actually it has probably even around 100 megavolts per meter. What is the limit is the breakdown of the vacuum. So in the accelerating structure, you start having sparks, and when the spark occurs, then of course it starts affecting the surface of the accelerating structure, and once the surface is affected, the sparks are happening even more often, and at some point you cannot, it just doesn't work anymore. So it breaks. One of the ideas for new acceleration is to use something which is already broken. So what is already broken is plasma. In plasma, we already have, plasma is obtained by a discharge, electric discharge. So we already use the very thing that stops us in RF acceleration, we use in plasma acceleration. Where in plasma, electrons and ions are separated. And when we shoot very strong laser pulse into plasma, for a very short time, electrons get separated from ions. They are moved by very small distance. Then they immediately come back. But if we manage to inject the beam in this very short time when they are separated, right after the laser pulse, then actually we can get local acceleration with the fields of the order of 100 gigavolts per meter, so 5,000 times more than what we get with RF acceleration. And currently there is a lot of work going on in order to master this kind of acceleration and make it actually useful. However, it seems to be really a long way in front of us. There are no easy answers. We can get some beams out of these machines, but they are very low intensity and very difficult to control. All right, so this is the summary of the last few slides. But let's go to the next part because we don't really have a lot of time. Now we go to the details of how a synchrotron, or in particular a synchrotron, works. First, we already discussed, it was already discussed yesterday, the beam trajectory is controlled by the dipole magnets. Dipole magnet is shown on this drawing. It contains coils. So on 3D, the coils, they look like that, right? It contains a yoke. Yoke is actually very important for normal conducting magnets because it allows to guide the magnetic field lines and to obtain much higher field than without the yoke. Without the yoke, you know, the field which is produced here will be very non-uniform and spread. So we always have this massive yoke, and we have those two poles of the magnet, and in between poles we have what we call a good field region. This is where we want our beam to be. We don't want it to go this way, because here we don't know what is the field. I mean, we know, but it's not well defined. We want the beam to start in the good field region. Now, another important concept here is magnetic rigidity. So the two particles which have the same momentum to charge ratio will bend exactly the same way in this magnetic field. So the bending radius will be the same, will be constant. So for instance, if in our machine we have carbon 6+ and helium 2+, they have exactly the same charge to mass ratio. And if they have the same momentum, then they will have exactly the same trajectory. This can be actually useful. Before I said that we usually accelerate beams of one type of particle, but we can actually have several types of particle at the same time in the machine, and we can use it in our favor. And actually, there are some techniques in hadron machines, in hadron therapy, which try to take advantage of this possibility of accelerating different ions at the same time. All right, then we go to beam stability, and we will spend most of the times on the beam stability now. When you think about the beam of light, which goes through a hole, through a collimator, a hole in the shield, then it's naturally divergent. All right, you have a hole which is, let's say, a few millimeters, and on the wall, a few meters apart away, you have a much bigger beam light spot. Now you can go around that if you put a lens in between your bulb and your screen. And actually, if you put a set of lenses like that, this is a typical setup of a camera lens, then you can very well control the beam. You know, you can zoom, you can change the focus, and this is something we would like also to have for particle beams. But before we go to this, how we do it for particle beams, the interested, curious student may tell me, well, but there are also lasers, and they stay collimated without any lenses, right? You have a laser, you can shine it on the wall, and the spot on the wall is basically the same as the spot which comes from the laser itself. The question is, can we do similar thing with ion beams? Unfortunately, not really, and there are very profound physics reasons for that. Basically, there are two. Well, the beam is made of charged particles, so there are Coulomb forces which act on the beam, on the particles, and that they make the beam naturally spread. You don't have the same with photons in the light beam. Photons, they don't, in principle, in the first approximation, they don't interact between each other. There is no repulsive force. And then ions are fermions, so are particles which don't like to stay in the same place, and this also affects the way they can be transported. So we cannot have a laser of ion beam. However, there's something which is called crystalline ion beams, and these are the beams where ions are actually ordered, so the distances between ions in the beam is equal, and they form kind of a crystal which moves forward, and this kind of beams, they actually reach the highest emittances and the highest beam densities, but they are very difficult to get, and they are not useful for medical machines. So let's go back to our lenses. Before we go back to our lenses, let's notice that actually there is a force generated by the dipole which actually stabilizes the beam. And here you see a cyclotron and the dipole field lines in the cyclotron. And when the particle is at the edge of the cyclotron, somewhere here, it travels, let's say, towards the screen. The beam line, the magnetic beam line are not anymore vertical, they are tilted, and therefore there is a force which has a component, I'm sorry, which is acting towards the center of the magnet, right? It will act exactly opposite here. So if the particles are vertically divergent, they actually get focused by these fringe fields towards the center of the beam. This is called weak focusing, and the first machines in 50s, like a Cosmotron, this is a synchrotron called Cosmotron, it was based on this weak focusing principle. However, soon afterwards, there was a strong focusing principle discovered. Actually, the first idea was even before 1949 by a Greek physicist who never published it. He patented it but never published. So it was rediscovered in 1952, and basically Cosmotron was probably the first and the last machine which was built without the strong focusing. Strong focusing is using basically the lenses to control the beam. What are the lenses for charge beam? Well, they are not glass lenses, they are quadrupoles. They are quadruple magnets, and we will see how. Now, we will have to know that quadruple magnets, they always focus the beam in one direction and defocus in the opposite direction. So let's say we have a quadruple which is focusing horizontally, and the same quadruple must be defocusing vertically. This we will see maybe on this plot. Here you see the beam lines in the quadruple magnet. We have the poles, 2 north poles and 2 south poles. These are the beam lines. In the middle of the magnet, the field is 0. So the good particles, they are not focused, neither focused or defocused. But if they are traveling outside of the beam line or of the beam center, they actually start feeling forces from those magnetic field lines. And those forces here are focusing, while here are defocusing. And there is no way around it. But fortunately, we know from optics that a set of focusing and defocusing lenses can have a net focusing effect. And this is what we are using. This is expressed by this equation, which shows the focal distance of a set of 2 lenses. And now if you take f1 equal f2 and you calculate, do this calculation, that you find that net focusing, so focusing of the 2 lenses, is equal to f squared divided by the distance between the 2 lenses. And this is of course positive. And this is the principle we use in the accelerators. So as I said before, the quadruple magnets provide focusing, and they are characterized by field gradient, which is expressed by this equation where you have current in the coils and number of rotations in the coils and the size of the magnet. This is important, and we usually normalize this gradient to beam rigidity, and we talk about K values, or K parameter. So this is very nice. We use it all the time for calculation of properties of accelerating structures, of lattice. We call it lattice, so focusing systems. All right, then, as I said, we need focusing and defocusing quadruples to transport the beam, and they are usually assembled in so-called cells. And one of the simplest cell is a photocell, focusing defocusing cell, which is basically exactly made of one focusing, one defocusing quadruple. And here you see one of the largest photocells that were constructed. It's LHC photocell, which is made of 1 quadruple, 3 dipoles, 1 quadruple, and 3 dipoles. The length of such a cell is more than 100 meters. All right, now if we want to understand what is happening with the beam in the accelerator, we have to create an equation of motion for the particles in the machine. I'm very sorry, there is somebody cutting grass. In order to do this, first we have to introduce a reference system. The reference system which we use in these calculations is a system where particle moves in the reference trajectory. So the trajectory which goes through centers of quadrupoles in principle. And we have S coordinate, which is along the machine, and X coordinate, which is horizontal coordinate, and vertical coordinate, which is epsilon. Equation of motion is expressing the position of particles in function of time, the position and the angle. As the particles move through the lattice with constant velocity, we replace time with a position along the machine. And when you look at these calculations, you will see that we can easily do it. And what comes out here is velocity of the particle. If we put this calculation into equation of motion, which is basically the Lorentz force here, then we get this red equation, which is an equation of harmonic oscillator. So we already know that the movement of particle, transverse movement of particle in the machine will be some kind of harmonic movement. And the solution to this movement is periodic because it's a harmonic oscillator and can be expressed by these two equations. For the focusing quadrupole, we find a similar solution, but with hyperbolic functions. In general, what it means that we have a particle which moves in the synchrotron, and actually it always oscillates around this reference orbit. Particle has to oscillate because there is no perfect machine, and even the alignment of the quadrupoles cannot be ideal. So every time there is a little misalignment, the particles, they actually get kicked and the oscillation is induced. Here there is a general solution of this for this movement of particle, and this general solution contains a beta function and the phase of the movement, and it also contains two values which are constant of motion, which depend on the initial condition. This is related to the beam emergence, as we will see later, and this is initial phase of the oscillation. All right.
Please switch off your microphones.
Hear me, because there is this.
We can hear you well. It's not really affecting. We can hear you very well. It's not really affecting.
All right.
But I ask all participants to switch off your mic, please.
All right. Thanks. I was thinking that you are getting the noise from outside of my window. Okay.
Just a bit, but it's not
all right,
loud
so
enough.
This oscillation of particle, transverse oscillation of particle around the machine is called Betatron oscillation, and it's the additional oscillation. So we had synchrotron oscillation, which is longitudinal oscillation, and here we have Betatron oscillation, which is transverse oscillation. And this Betatron oscillation follows a beta function. So the amplitude of the oscillations are not always the same. And here are the typical plots that you get when you have a transfer line or a synchrotron. The left plot is for transfer line, the right plot is for synchrotron, and this is a distribution of the beta function along the machine. So the beta function is, of course, separate vertically and horizontally, and this beta function is defined basically by the strength of the quadrupoles. Strength of the quadrupoles. And we can change it. In principle, we can have different working points. We will talk about it in a moment. Now, there are two very important concepts. All the important concepts kind of come at the end of the presentation. One is the phase advance, which is the phase of the Betatron oscillation from one point to another point. And it can be expressed as this integral over the beta function. And then the total phase advance in the synchrotron is called the tune. So tune is how much phase advance the particle is getting after going through whole circle of the machine. So you see it's a very similar equation. It's just the integration is over circumference of the machine. Here you see the phase advance of LHC photocell, and it's actually around 90 degrees. So why tune is important? tune tells us how many oscillations a particle gets when it goes through the circumference of the machine. Now imagine that there is, because there is always some misalignment or other perturbation to the movement of particles. This perturbation happens, let's say, in one magnet. So in this location, the particle always gets the same kick, transverse kick, because of this error, this bad construction, the micrometer change of alignment of the quadruple, for instance. Now, if the number of oscillations is integer, so let's say 5, then particle will arrive to the same error with the same velocity, the same angle, and it will get the same kick again. So basically it will blow, it will not be stable. It's like how you call it? Yeah, okay. It will always get the same kick, and this behavior of this particle will not be stable. Machine will not store the beam. So we cannot have integer tune. Actually, we cannot even have half tune, because some errors, even if they are repeated every 2 orbits, they also lead to blow up of the beam. And also the third integer, usually we don't operate with. I hope this is clear. Here you see something which is called a map, a tune diagram of one of the machines in GSI. And you see this, there are lines. So this is, for instance, line where horizontal tune is 4. And you cannot operate at tune equal exactly 4. Yeah, actually, this is a measurement, and you see that what you think, this is a theoretical value, and this is the real line, which is right next to it. So it only shows that in this particular measurement, our model of the machine was not very good. But you cannot operate machine at certain tunes, okay? The blue areas is the areas where you can operate your machine. So this is bad, but this is also good. And Rebecca will talk about resonance law extraction on tomorrow, right? So if you want to extract the beam from the machine slowly, you actually want to excite the beam. And therefore you can operate at very close to the tune, and the beam, the particles in the beam will be excited and will be extracted to the patient.
I have 5 minutes left.
Yes, thank you. Then another important point is the dispersion. Dispersion is basically if you have particles with 2 different momenta moving inside the dipolar field, then of course they will have slightly different trajectory. And this change of trajectory with change of momenta is called dispersion. We have also similar thing for the angle. So change of the angle with change of the momentum is dispersion prime. The dispersion, obviously, when we have it, it leads to the increase of the beam size. So the actual beam size, the equation I gave you before was only containing beta function and emittance, but this is increased by the fact that we have dispersion and there is certain momentum spread of the particles in the beam. Obviously, dispersion is related to dipole magnets. So it is created by dipole magnets, but if we change this dispersion prime can be changed by quadruple magnets, then actually we can control the dispersion. And what you see here is a beam coming to the system without the dispersion. It goes through the dipole, quadruple and dipole, and then comes out also without the dispersion. This set of magnets is called double band achromat. We really like places with 0 dispersion, but we also like places with measurable dispersion. And here is an example. Similarly to the dispersion, if the focusing of the quadruples depends on the energy of the particles. So if the particles have slightly larger energy, they will focus in a different place than slightly lower energy. And this is called chromaticity. It's actually also known in optics, right? In normal optics. For the circular machines, we say that we define chromaticity as tune prime, and it is change of the tune with momentum of particles. And we can correct it using sextuple magnets. So this is how the sextuple magnet works. We have this error of focusing because of the chromaticity of the quadrupole, and this error is corrected by this particular shape of magnetic field, which is produced by the sextuple magnet, and we focus again correctly. This will be important also in Rebecca's talk. And note that here, for instance, this works only for quadrupoles which are placed in dispersive region. If we don't have dispersion, this correction will not work. All right, then I'm coming to the end. I think I will be a little bit late, but this is really important. We discussed the beta function. Now, the slope of the beta function with the machine is called alpha function. This is the definition of the alpha function. And sometimes we also define a gamma function, which corresponds to beta function, but for the angle. These three functions, alpha, beta, and gamma, they are called twist parameters, or sometimes people more aware of the history, they like to call them Courant-Snyder parameters. And they are very much related to the beam ellipse. Here you see the relation. So this is the beam ellipse. It has a certain emittance. The beam size here is defined by the emittance and the beta function. The dispersion of the beam is defined by the emittance, beta function, and alpha function, right? Or no, even here, it's, yeah. All right, so basically knowing the emittance and two of the three parameters, because the third one depends on the alpha and beta, we know everything about the beam. Now, in order to transport the beam, we use something which is called matrix formalism, and this is a very convenient way to transport the beam through the machine. For instance, this is the matrix element of the focusing quadrupole, and here is its position and angle of the particle inside the beam. If we multiply it by this matrix, then we get the position and the angle of the particle after quadrupole. Each element has a matrix, and we can have a total matrix by multiplying a lot of matrices, and like that we can reconstruct the trajectory of the particles. So we don't really have to do real tracking in real fields. In this approximation, we already get ideas about how beam behaves inside accelerator. And my last slide, I hope I'm not too long, is about the beam ellipse or beam matrix and the beam transport in 6 dimensions. So first of all, the equation of ellipse can be written in the matrix form. So basically here x is a vector, x prime actually, sigma is a matrix, and this is this matrix, we call it beam matrix, and this is vector which is transposed and a vector again. If we write equation like that, if we write it linearly, then we basically get equation of ellipse. So so the beam matrix, this sigma, basically describes the beam ellipse at a given position. It's very nice because instead of having positions and angles of all the particles in the beam, we can actually have just one matrix. This matrix actually has more dimensions because it's two parameters or 2 dimensions in X, 2 dimensions in Y, and also we have 2-dimensional longitudinal phase space. So altogether, the beam matrix has 6 dimensions. Here you recognize horizontal beam ellipse, vertical beam ellipse, and this is longitudinal beam parameters. And these parts are couplings. So this is the coupling with the dispersion, right? So horizontally, it's important. Vertically, it's usually disappearing because we usually don't have vertical dipoles. All right, so basically, this is my last slide. And this was the introduction to the accelerator physics. I go right to the conclusions. I hope I convinced you that accelerators are one of the most important tools in science, medicine, and industry. They produce beams of particles with given energy and emittance. The two very strong concepts, very important concepts are RF acceleration, which allow to reach high energies, and strong focusing, which allow to control the beam in the best way. And then other important concepts related to beam dynamics is elementary cell, twist parameters, beam phase space, longitudinal and transverse, beam ellipse, dispersion, tune, resonances, chromaticity, and the matrix formats, which is used for beam transport. And I hope it was not too confusing for you, and thank you very much for your attention.
Thank you very much, Mariusz, for that very comprehensive and very well presented introduction to accelerator physics. We are running late, but I would like to give some time, just 1 or 2 minutes at least, for questions.
Mariusz, if you could please stop sharing so that we can post the file with the questions. Thanks.
Okay, I don't think we will go through all of them. Maybe we can go through.
We can also do it. I don't want to disrupt the schedule. We can also do it maybe in the afternoon, or
yes, we have time for discussion in the afternoon, but just a couple of them, and the rest we discuss it in the afternoon, right?
All right. So the first question is neutron decay time, which is around 11 minutes. Is it why we must wait some time before entering our accelerators after switching off the beam? Actually, yes and no. No, because usually neutrons are never stable. I mean, they don't stay like that. They are usually absorbed within few microseconds by some nuclei, but these nuclei which absorb them, they became unstable. So there is a certain decay time, and these decay times are usually much larger than 11 minutes. So usually we have to wait more before entering the accelerator. It really depends on what kind of beams we had in the machine and what were the beam losses. All right, so yeah, it's not directly related to the decay time of neutron, but it's related to the decay time of isotopes, other isotopes which are produced in accelerators. Then there is a question, momentum to charge ratio, is this what we refer to as gamma? No, I was really not clear in my presentation, I'm very sorry. No, momentum to charge ratio is, yeah, it's just a momentum to charge ratio. Gamma, we have two gammas. There is relativistic gamma, which is basically a ratio of relativistic energy or total energy to rest energy of the particle. And we have this gamma, which is a twist parameter. It's also a little bit confusing that we are using the same letters for two. I'm sorry for that. Maybe I should clarify it a little bit more. So yeah, it's the second answer to the second question is no. Why is normalized emittance conserved during the acceleration? What is the physics behind it? Yeah, so the best to explain this would be to do a short calculation. It's the relativistic physics which is behind it, and when you look at how the transverse and longitudinal, transverse components, they don't compact. Transverse movement is not affected by relativistic effects. Longitudinal is. And when you correct for these relativistic effects, basically by using beta and gamma, so relativistic parameters, then you correct for the increase of the movement. I mean the acceleration of the particles, and then you stay with normalized emittance. Should I go on?
We will continue up to, well, for another 2 minutes, and then we'll proceed to the next speaker.
So the question number 4 is, I think the Liouville theorem is explained the emittance conservation. Yes, the Liouville theorem is explaining the emittance conservation. This is basically true, yeah. The question number 5, when we use the degrader, the emittance of the beam will increase. Is there any way to limit the increase of the emittance? Yes. So first of all, you try to focus on your degrader if you can, because sometimes the beams have so much energy that if you focus, then you destroy the element. But if you focus on your target, then in principle, the particles which are coming after the target have the smaller emittance increase. You cannot avoid it, but this is you can minimize it this way. And in order to understand that, yeah, maybe contact me, and it's a very simple drawing, but I really have to draw it to explain it. Otherwise, of course, after the degrader, we have collimators which remove large part of the beam. In cyclotrons, sometimes even 90% or 99% of the beam is actually useless, is removed in order to get the beam that gets to the patient. Okay, the question number 6, from synchrotron, we get asymmetric emittance. However, to get gantry angle independent on beam optics, it is required to have the same emittance in both axes. How do you make emittance symmetric? All right, so this is actually a question which takes quite some time to explain. Maybe I leave it to Elena for tomorrow, because she will be talking about the gantries tomorrow or on Thursday. Now I don't remember. And this is exactly one of the things that I think she will address. Why do medical cyclotrons have constant extraction energy? This is also a very good question. Well, in the cyclotron, basically, you know, it's a fixed structure. You accelerate the particles and you don't really have a way to extract them before you reach the end of the cyclotron, right? Your extraction devices at the edge of the cyclotron. And there is nothing you can do. You cannot decrease the frequency of your field, because you will be out of synchronous condition. You cannot decrease the voltage between the electrodes, because then you will be again out of synchronous conditions. So cyclotron is a simple device, much simpler than synchrotron, but you pay in flexibility. You just have to extract the energy at which the cyclotron is designed for. There are some tricks, but so there are some tricks that people do to extract at different energies, but they are difficult, they are experimental, and they make everything much more complicated.
Mariusz, I would like to thank you for your presentation and for addressing these questions. And